thank you all for joining us. I'm going to stop sharing my screen so you can see
Yes.
my big head. And now, let me
They
just
say the bigger the head, the bigger the star.
Yeah. That's it. So the idea here that we have today, I hope everyone realizes this is not going to be like a traditional meetup. We've got Dan joining us, and he is going to go through a workshop. So it's hands-on, it's interactive. It is the first of its kind in this MLOps.community meetups, we could say. And so I'd love to hear your feedback on how it goes. I want to intro Dan real fast because we met actually when at ODSC last year, and you were presenting there, and
Indeed.
then we talked about kind of the data science world and where you saw things, and I remember talking about Databricks and also very much how volatile things are in the data science world, and especially in the data science tooling space, because we were mentioning, I think I tried to sell you dot science. I tried to sell you on it. And then you were like, yeah, I mean, I try to stick with open source stuff these days because it's just very crazy what's happening out there. And you called it because then dot science went under. And so sell you on it.
It was the red. I think I said the risk side of it, right? Like if it goes under, then you have to rewrite all your code, which I've seen happen. So.
Exactly, and it happens, and there's a reason that you are experienced and wise in that sector. So, but that's not what we're here today to talk about. I mean, you have been teaching all over the place. Maybe you could give us just a little bit of background on what you've been doing with teaching, and then what we're going to go over today, and I'll hand it off to you.
Yes. So, quick background on me. I mean, I actually started my career in quantitative finance quite a few moons ago, and did that for about half a decade, and then worked on the consulting side of things, running a small consulting shop for about 10 years. These days, I'm like heading up a data science team and also doing training. Most of the training work I do is kind of either for organizations or companies internally, or also I teach through O'Reilly and Pearson, through the O'Reilly.com platform on a fairly regular basis, and also at conferences like ODSC, where I generally teach about a lot of the toolings behind doing data, not even necessarily data science. Some of it might be just be data engineering or building out data-driven processes. And if I try to pick as an audience people who have a background perhaps in software, but not necessarily in working with data, so that these can be fairly accessible to a lot of people and kind of get more people interested in it or using it just in their day-to-day work.
So this is an adapted version of a longer course, right?
Yes. So this is what we're going to be going over today. Is that I recently created a new course that is a DataFrame focused version of using a library that we're going to be going over today called Dask, which I don't know how many people are familiar with it prior to this, but it's effectively a distributed, well, it doesn't necessarily have to be distributed, but you could say a graph execution framework that's completely written in Python. So unlike using something like Spark, where even though you have PySpark that can go on top of it, that's essentially going to be a wrapper that's calling all this underlying JVM code. And if you've ever seen a stack trace from Spark, you will understand, you will know what I'm talking about. There's a lot of layers underneath what you're doing. And with Dask, it's a little different because everything is written in Python, so you're using pure Python code throughout the entire stack. So conceptually, it's much easier to work with since the model that it operates on is much simpler.
Perfect. Now we will, I guess I'll let you just get into it, but as we mentioned before, this is like going to be an hour and a half,
Yep.
and the full course is about 4 hours, you mentioned. And so if you want to go and check that out, we can put a link to that at the end. So if you're really feeling like, whoa, this is cool, I want to learn more and go deep dive, then we'll throw a link in there. Now, I'll let you take over, Dan. Thank you for that. And thank you for coming.
Yeah, no, of course. Happy to be here. All right. Well, we'll just jump in from there. I'm going to probably share my screen for most of this, just as a lot of it works kind of as an interactive demo, especially for working with Dask, where a lot of the things and the usefulness of the framework is that it has all these great diagnostic tools with really cool visuals that don't work quite so well if you're using slides because you can't see the animations, things like that. So I'm going to switch on the screen sharing now. Just one sec. And all right, you should be seeing my Chrome browser now. And so I'm in the GitHub repo here. So all the code for this course is available here. In addition, some that we're not going to necessarily have time to go through today because it's more part of the 4-hour course. But we're going to be focusing on the kind of initial 1.5-hour version, which could it's kind of like a crash course in data frames with Dask and going through kind of the most important components. We're not going to go through as much of in the full course. We also go through really like what are the main differences in the APIs between Dask and pandas, because the Dask, so one benefit of Dask is it under the hood basically uses pandas. So we'll see as we go through that basically we're just working with a bunch of distributed or partitioned data frames. So there isn't a new mental model you have to learn. You're just working with things that you're familiar with from your day-to-day data science work. So the repo is up here. It's also in the Q&A and chat there. And if you want to, you can follow along with everything here just by, you can either open up the individual's IPython notebooks and then GitHub will pre-render them for you. Sometimes it doesn't always work. Sometimes you have to reload it, but this is also a pretty big one, so it might take a second. Otherwise, if you want to run everything interactively, you can actually start up the binder link here, and then you'll just be able to follow along directly in a Jupyter Lab notebook that it's going to set up for you. The only difference is going to be that some of these things are using, as we'll talk about shortly, what is called the distributed scheduler for Dask. And this is a scheduler that will actually let you run Dask across a cluster. That's not going to, I believe will work in Binder, but of course it's only running on a single machine. So there's less benefit. And I don't think you're going to be able to do things like get access to the dashboard in there. So it's more just, it will get you up and running relatively quickly once this gets started up here. But just a heads up for some different ways that you can run everything here. And there's also instructions if you want to set things up locally, you can do that as well. That's generally how I recommend running this, but it can take some time to download Miniconda and get everything installed. So I will leave it up to everyone in terms of how they want to get things going. Binder can take a second to get started, but that's probably going to be the quickest way to go. And you can see here, this also, we got everything to run on here as well. So. All right, so what are we going to be focusing on today? So as I mentioned, Dask is a library that you can think of for parallel execution or asynchronous execution on task graphs. And that seems kind of abstract, but generally what all of these distributed computing framework let you do, even things like Spark, is they'll generally let you put together different computations using their specific operators, and then they will figure out what is the best way to execute it. And you can give them different levels of instruction about how they should go about and do this, but Dask is going to be fairly low level on doing this. So it's kind of an arbitrary, it has very low level primitives that will let you define your task graph in a very granular fashion, much more granular than you could do with something like Spark. So while this will allow you to have certain optimizations or allow you to define certain and solve certain problems that you can't solve with Spark very easily, it also at the moment doesn't have some of the higher level optimizations that Spark can have. Like there's not going to be a SQL engine in Dask, although there are some projects like Blazing SQL that are looking to add this or have added part of it. It's not going to be as built in and unified as something like Spark is going to be. So the side benefit, though, is getting started with Dask. Since it is written in Python, it is very easy to get started with, and you can run it on a single machine or a bunch of machines. But getting started with a single machine is going to be very easy. And so if you follow the local or the instructions for setting everything up locally, you'll end up installing actually for Jupyter Lab a Dask plugin. And what this is going to let us do is with a single button, start up a cluster on our local machine. And I mean, we could, again, do that. Well, actually, let me take a step back from there. So there's an even easier way to set it up, which is working with this distributed scheduler we're going to be doing today. To just start up a cluster on your local machine, all you have to do is actually import this client and then instantiate it. And then you're going to have a cluster running on your local machine. And we can actually take a look at it here. Let's say fresh should come up now. So we're going to have our little task stream here, which isn't going to have anything on it yet because we're not yet running anything. We can bring up our progress dashboard here, but again, we haven't done anything yet, so we're not going to see anything up here. But as soon as we start doing some work with Dask, we're going to see how this comes up. And so we can take a look at our client here. So this is telling us here that we have a Dask cluster running on our local machine. So I mean, it's not really a cluster since it's only a single instance, but we're making available to it 4 cores or 4 workers. It says 8 cores because it's using 2 threads per worker, and that we're making available all the memory on my laptop of 16 gigs to the cluster here. And since we're going to be working with the DataFrame library today, instead of importing something like pandas only, we're also going to import our Dask DataFrame library, and this is going to be Dask DataFrame as DD. So this is a fairly standard alias that you're going to be using for it. And I've already loaded in a data set here that I formatted a bit. There's actually a lot of data available from the New York City data API, and this one is actually how much people have gotten paid in New York City over the past few years. And so I've already gone through it a bit and specified the data types just so that we read it in kind of without any errors and not using as much memory. And so this is all specified for you here. And now we're going to do our first Dask call here, which is instead of using pandas read CSV, we're going to use Dask read CSV. And one thing you're going to notice here is that when we're using Dask, we can actually do something that gives us a wild card in terms of reading in files. So we can read in more than one file at a time with Dask. So this is going to be the first difference that we're going to see, where we get this blobbing ability. And we're going to run this, and as you may have noticed, it returned very quickly. And the reason for this is, in general, Dask, when you give it a function to execute, is going to do it lazily. So it's not going to actually execute anything until you tell it to do so. And so the first thing we're going to look at is our underlying D types here for the data frame, and we'll see that this works mostly like we would see in pandas. And we can even take a look at the top of the data frame, and you'll probably notice here on the side that a few things started to happen in our task stream. And so what this means is Dask went ahead and read for one of the partitions of our data set, called these two different functions here. And we'll start to see as we do some more serious computation that we're going to start to be able to use more than one core at a time. So here, since we're only, when you call head, actually it's only going to look at the first part of the data frame here. And the reason for this is, as I was mentioning a little bit, that Dask data frames under the hood are just pandas data frames, except they are partitioned into multiple smaller data frames. So this diagram here, that's actually from the Dask site, shows how this works, where you're going to have this one larger logical data frame. And it doesn't have to be broken up by time, but you can set it. I mean, you can also just have it be broken up by integer indexes if you didn't have something meaningful here. But you're going to have this partition data frame in memory on a single computer or across a cluster. And this is where you're going to get your parallelism from. And what will also allow you to work on data frames that are larger than one that you could fit in memory, because you're then just going to be able to chunk over it iteratively. And one of the big benefits of Dask is that you can have Dask do this for you. So Dask will take care of performing this chunking for you, so you don't have to manually code it out. Because of course you can always read a CSV file incrementally or split something out and read one part at a time, but Dask is going to come up with ways for you to do this, and by working directly on this graph that we're going to take a look at next. And so one thing I've mentioned a few times, and which can seem slightly abstract, and as we're going through this, don't worry too much if parts of this seem a little confusing, because there's a lot. I mean, we're starting with one of the slightly higher level APIs, which is the DataFrame, versus just going with base Dask. And also we're kind of diving in deep right away. But by the time we get through to the end, it should all really come together. And we'll be going, so if part of the things where I'm talking about the task graph or the partitions like that don't seem a little confusing at worth, try to stick with me, because we will be explaining them in due course. But there's a few things we have to get through before we can really show what Dask is built to do and conceptually understand how it's working. So like I mentioned, what Dask is going to do for us is it's going to create this directed acyclic graph. And what that means is it's going to have a series of functions that it needs to apply to get to our end state. And so this is going to be different than something like pandas or regular Python that you're using, where you write some code and it just happens immediately. With Dask, it is going to build up the graph of computations and then execute them when you tell it to. So if we take a look at how our function for reading a CSV is working, you're going to see that we have these 3 read CSV calls, which one is going to be for each partition of the data frame that Dask has decided it's going to read in. And so you can think of, we're going to have 3 of these like in this graph here. And then this is going to result in outputs. And again, this has not happened yet, but we're still going to have other information available, like the number of partitions for our data set. We can look at and see that here there's going to be 3, and this is going to correspond with our underlying task graph here, which we're looking at by using this visualize method on it. And the ranked here just lets us specify the direction that the graph is printed out in, but you could have it top to bottom as well. It's easier in the notebook to show it left to right. So we let Dask determine the number of partitions automatically, but it has a default size it's going to use. But you can also see that in general, this is going to be based on the number of underlying files that we're reading in and also the size of each file. So here we're going to specify a separate block size that's going to be 0.5 MB. And then if we take a look at this, we're going to see that we now have a number of partitions that's 22. And so this is going to be Dask telling us that in order to read in this CSV, we're going to start out by breaking this up into 22 sub data frames. And this is how Dask is going to then be able to distribute our work and do it without running out of memory. It's going to split up into smaller parts of work that don't require us bringing the entire data set into memory at once. So once we have this graph, the next thing we're going to want to do is to schedule some computation on it. So let's do something that looks just like a regular pandas operation, like calculating the max base salary here. So one thing you're going to notice is that when we calculate max here, like I've said, it's not going to give us an answer. So what it's actually just given us is another graph output. So to actually convert this into an answer that we want, we're going to have to tell graph to do the work for us. And so we do this by calling compute on the graph. And so let's do this now. And we're going to see that some work now appears to have happened in our task stream here. So you can see now that we have some tasks for reading the CSV by chunk. This has been done in multiple workers here. Each bar here is going to be a worker. And we'll go into this, how this scheduler works and these diagnostics a bit more later. And then there's other operations that we have called on them here as well, where we're getting the max for each chunk, and then we're transferring data to another worker, and then we are calculating the max of that series here. So each bar here is a separate task that Dask has split up for us. And out of this computation, what seems something relatively simple, just reading in a data frame and calculating the max of a single column, Dask has broken this up into multiple pieces, parallelized it for us across multiple processes, and then brought all the data back together. So it's done a lot for us with a relatively small amount of code. And we can actually take a look at what it did for us under the hood by printing out the graph again here. And so we're going to see our job starts with a low-level read CSV call here, or I guess it's relatively high level since it's reading. It's not like reading a block of bytes, something like that. And then it's going to call this get item function that's going to extract out the individual column we want. And then from each of the chunks of data, it's going to calculate the max and then combine those maxes together. And so, again, Dask has created this computation graph for us. It's not going to evaluate it until we tell it to do so, which allows you to build up an arbitrarily complex graph of computation. And then once you have this built up and know that it's going to operate in a way that makes sense, you can tell Dask to then go out and perform the operations it needs to do. And it will figure out, in cases where it's possible, how to do things like parallelization, things like that. As you can see, like within this graph, there's 3 different separate streams of possible work here. Like each of these read CSVs can happen in parallel because they don't depend on each other. It's only once we get up to this max aggregation that we need to have all those prior results done. So by having this graph ahead of time and having a framework that is smart enough to operate on it, you can get benefits like parallelization without having to explicitly tell the computer how to do it. Dask is going to figure it out for you effectively. Now, one thing to note is that because Dask operates lazily, it has not actually persisted anything into memory here. So you'll notice from our graph here that even though in the previous case, we had read the CSV and looked at the head of the CSV, like the first 5 rows, when we call the max here, we are seeing again that the CSV is being read from scratch. And part of what allows Dask to work out of memory is that it doesn't explicitly store things unless you tell it to. So in a sense, you can't have it both ways. You can't store everything in memory and then expect it to also be able to work out of memory. So in cases where you do want to persist part of your data in memory so that it's available for future computation, Dask will let you do that, but you're going to have to tell it to do that. It's not going to know a priori that you want to cache something. So there is a method that's going to do this, which is called persist. And what this is going to do is to tell Dask that, hey, we want to basically store the results of these computations on the cluster, and again, the cluster can just be your local computer. It doesn't have to be more than one computer. And in this case, since I'm running this on my laptop, it is just my computer. But store this in memory. And now if we take a look at our Dask or our graph now, you're going to see it's just 3 rectangles. And that's because we've taken the results of these read CSV computations and just stored them in memory. So now the only graph we have left is just 3 partitions of a data frame in memory. And we can see how this has happened again if we start from our persisted graph, and we're going to calculate max again. Notice this is, until we call execute, this is still just going to retrieve a new graph for us. And now when we look at our graph again, we're going to see that the read CSV part of it is gone. And the reason for that is we're starting from our in-memory representation, so we don't have to get all the data from disk again. Have any questions so far on what we've gone through? Feel free to put any questions in the Q&A or chat. Q&A is probably easier since it won't scroll by. I see someone has, can we have a TTL and persist method? I don't believe you can specify a TTL, although in theory, Dask should. I believe it will remove data after a certain point if you're reading in new data. So in a sense, if you add additional data at some point, I think it will remove kind of the most recent or the least recently used data, but I don't think there is a explicit TTL that you can set to any data on there, at least at the data frame level. Any other questions? I'll just put them in the chat or QA, and if it makes sense to answer them, I will as we're going through. Otherwise,
yeah, and I can also keep my eye on it in case something jumps up, and then I'll let you know.
Yep. Thanks. So next thing we're going to look at is just comparing this to how we would actually do this in pandas without using Dask. So I see someone has a question. What is the difference between Dask, koalas, and PySpark? So koalas and PySpark are both Python APIs for Spark. PySpark is going to map fairly closely to the general Spark DataFrame APIs. Koalas, I think I haven't used it, but it is supposed to be more similar to the pandas API, except for Spark. So those are both Spark-based libraries. Dask is a separate framework. So Dask is going to be fully written in Python as opposed to Spark, which is in Scala and on the JVM. And Dask is going to integrate more closely with other Python projects like scikit-learn, or you can just, at the simplest level, just write regular Python functions and use them directly in Dask. You can't really do the same thing with PySpark because everything is running directly on the JVM. So a lot of Dask or PySpark functions are actually just calling different Java methods directly or Scala methods directly. You can have Python code that gets run within PySpark and Koalas, but most of the time what's happening is that you're running a separate Python process and data is getting serialized into it and then evaluated from Spark. So when you're using Dask, everything is just happening directly in Python. So it's going to be you're working within a single language for the most part. And it's going to wrap most of the Python APIs you're familiar with, from including pandas, which we're looking at now, as well as having APIs for arrays that are like numpy, and then just the lowest level delayed libraries, which we're not going to really get into today, but at the lowest level, they work similarly to the concurrent futures and multiprocessing libraries. So you can basically use it to parallelize or work with arbitrary Python code asynchronously using these graphs. So hopefully that answers that question. All right, let's take a look at how we would do this in pandas. And we're also gonna, as we're going through these, I'm gonna time these to show what some of the timing differences are between running it in pandas versus running it in Dask. So since pandas doesn't have this globbing feature that we have in Dask, what we're going to have to do is actually use a file system path and then call glob on that to get the underlying files. So we're going to do that. Then we're going to read each data frame separately and then concat them together. Now, of course, there's ways we could do this more efficiently in pandas. Like we could read each data frame and just extract out the individual series, things like that. But I'm just trying to make this relatively simple. And so we're going to see that running this, I mean, in pandas is going to be pretty fast. It's 375 milliseconds. And then once we have it in memory, it is very fast. So just to calculate the max is going to be 1.35 milliseconds. On the other hand, running this in Dask, even though we have already persisted this to the cluster, it's going to take almost 50 times as long to run, because using Dask is going to give us this additional overhead of having to coordinate between different processes and serialized, deserialized data. So there's no free lunch to some degree with any of these things. Like using something that is more complex is going to have more overhead. However, if one thing I would note is if we just ran this straight from the start to the end and weren't reading the data in, it would run faster in Dask because we'd be able to parallelize it. But in cases where you are storing something in memory and then hitting it repeatedly, if you have a data set that fits in memory, it's going to always run faster using the in-memory solution as opposed to the distributed solution, just because there's always going to be less work that it's doing. So it's one important point I want to make, that if you can avoid distributed solutions, try to do so, because as I believe they say in the documentation, that parallelism is an expensive solution to computational problems that could otherwise be solved in memory or using a faster algorithm or compiled code. So we've seen a few of the output from Dask distributed, but let's take a little more look at a slightly more complex calculation. And one thing I'll note is that if you're not, so you don't have to use this Jupyter Lab output for Dask. If you want, you can actually just open it up in a separate tab. So if you click on it here, you'll see that it opens up a separate tab that has some other information in it. And we'll go through this a bit more slightly later about what these different things are. But it can be useful to have them all in the same window. So we're now going to do a computation that is going to calculate some grouped statistics. So we're going to calculate the mean and size here. And let's see, so we'll go back here to our status bar here. And so we're going to see then that we have our tasks here that have performed these aggregations. We again have some transfer data, and then we're going to extract out the transferred values. And let me see, I'm probably zoomed in here, which is why we didn't see it here. So if I hit reset here, this is going to again bring us up to the top here. So basically how I have this structured is, after this section, there's a short section of exercises that everyone should be able to do on Binder. And so I'll have everyone go through those, and then I will go through and solve them. And then after that, we'll go through a quick session on using the scheduler diagnostics here. So I've already mentioned a bit about this, of why we want to use Dask. Primarily, the reasons are going to be that we're going from kind of Python all the way down, really. So unlike things like Spark, where there's this JVM under the hood, in Dask, we're just using Python top to bottom. So everything from the workers through to the scheduler is currently written in Python. Although they may, for performance reasons, they are looking at writing parts of the schedulers in a compiled language. But at the end of the day, that shouldn't change how your Dask code is being written. You can also run Dask on a laptop or on a cluster very easily. So you can run it on HPC clusters, on your existing Yarn clusters pretty easily, or even just over a bunch of instances that you connect to with SSH. So it's very easy to deploy. Basically, all you need to do is be able to run these workers. You don't need an HDFS file system. You don't need something like Yarn running. If you have it, you can use it, but you don't need any of these things. It's very lightweight to start and then scale up. When to use Dask, again, is going to be, there's a few different cases. One is going to be if your problem does not fit in the memory of one machine. And this is probably going to be the most common reason to use it, because you'll be able to use Dask to, as we've seen, partition your data up and then compute on it in a chunked fashion. And because of how Dask understands how the graph works, it can also do this in a parallel fashion as it works through. Additionally, Dask, since it's going to give you, we're not going to go into this as much today, but since it gives you much lower level control, you're going to be able to basically put any arbitrary computation within Dask, as opposed to if you're using Spark, basically the highest or the lowest level primitives you have to work with are things like map, filter, and reduce. the end of the day, you're basically working on top of Hadoop MapReduce. So you're at a higher level of abstraction. And as I mentioned, that I think I like this quote so much that I put it here, that parallelism and distributed computing are expensive ways to accelerate your application. This is directly from the Dask documentation. So if there are cases where your data fits in RAM, then fit it in RAM, or if you can profile and rewrite parts of your code and compile languages, then you probably want to do that too, because Dask, or any kind of distributed computing will enable you to solve your problem or may enable you to solve your problem. It's always harder to run things on more than one machine as opposed to one machine. All right, well, let's everyone take a few minutes now and work on these exercises here. So you should be able to start these up in Binder directly. We have these 0-1 exercises. Let me start up my, hopefully this will launch faster now that we kind of warmed it up before. A lot of times, since Binder is a free service, it isn't always the fastest to start up the first time because it has to build your container and things like that. So in the meantime, any other questions people have? My dog has had a question, I guess.
I heard that one. That was good.
Okay, let's see. On Binder. Let's see. Claims it's launching the server here. So does anyone else have success in getting a Binder going here? Oh, there we go. So yeah, you can run this just directly here and exercises here. So I'm also, if you're running this locally, you can use the distributed scheduler, which if you don't use that, you're not going to have access to those cool dashboard graphs that we looked at. But for running it on Binder, it's easier just to not use that. So let's say it will take about 10 minutes to work through these now, and we'll, Demetrios and I will hang out here. We'll take any questions people have as they're going through it. That sounds good.
So I have a question for you, Dan.
Yep.
While everybody's working on this, what made you start looking into this? How did you find out about it, and why did you want to go deeper in it?
I think I first heard about it. I mean, Dask, I think, may have started in 2015, maybe. It may have started before that, but I think I first heard about it in 2015 or 2016. And it was intriguing because it's a pure Python solution and doesn't require you at a conceptual level. It's easier to understand than Spark. One issue with Spark is that as soon as you hit like a wall of performance, a lot of times you quickly need to become a Spark expert. So it's very, you can definitely use it to solve very large problems, but in most organizations, there aren't necessarily people who have that level of expertise in Spark. Like if you're Facebook or Google, you already have those people, but most organizations, especially in data science groups, are not going to have that level of expertise. So Dask is much easier to understand in terms of what's going on because the conceptual model is much simpler. It's really just that diagram we looked at, which is you've got a bunch of data frames that are partitioned. And so and you can look at the task graph, and the diagnostics for Dask as well are much better than I think what's available for Spark too. So it's just much easier to understand what's going on. It's in pure Python, and it's increasingly been adopted on the Python side of the world across different libraries. Like there's integration with scikit-learn and Rapids AI, which is the GPU accelerated DataFrame libraries out of NVIDIA are using Dask for their multi-GPU. So it's really been adopted, especially in the past few years, as kind of the place to be for this kind of distributed computing in Python, I think.
And are you trying to use this whenever it's necessary instead of Spark? Or do you still have use cases where you're using Spark?
I mean, there's still use cases for working with Spark. I mean, ideally, I would go to Dask first these days. I mean, the benefits of Spark, are still going to be to some degree like integration with like Hive data catalogs, which like they do have now in Blazing SQL, which is like a SQL layer that it doesn't necessarily use Dask, but it builds on Rapids AI. Like within Dask, there isn't something like Spark SQL directly, and the underlying DataFrame libraries are going to be better optimized within Spark out of the box up to a certain point. The issue, Spark 3.0 just came out as well, and that also brings in a lot of optimizations in terms of like setting the more optimal numbers of partitions and things like that. And these were things that I think should make Spark work better out of the box, hopefully. But yeah, like if you can put everything into DataFrame operations, then there are probably going to be cases where you can process more data in Spark with less resources, only because Pandas is going to be using, Dask is going to be using Pandas under the hood. If you're using the Rapids AI ecosystem, then and using those DataFrame libraries, you probably be able to even get better performance than Spark. Like they just released some benchmarks out of NVIDIA doing, I think the TPC benchmark suite, and for like price, I think they beat everything from a performance standpoint, and they compare quite favorably to CPU-based workflows, which are Spark, where Spark is right now. So if you can go GPU, then I think you're going to beat anything CPU-based on these kinds of things. And currently, that's not available in the Spark ecosystem. So that's also, I think, additionally why a reason to be watching Dask, and is it's going to be kind of the multi-GPU layer for a lot of these.
That's fascinating. So I'm also wondering what other kind of, since you're checking out all these different frameworks and you're looking at all this stuff all the time, what else excites you right now?
In turn, like any specific areas you're thinking, or?
I would just love to know if there's something that you have been playing around with lately and you're like, ooh, this is interesting. This could change things.
That's my dog just wants to know too. I think, I mean, the GPU accelerated libraries, I think, are very exciting. And they're largely like the Python bindings for those. I mean, Rapids is pretty new, like under 2 years old, but I think those are very exciting, and especially the ML acceleration and how quickly you can implement some of these ML algorithms on those relative to the CPU-based versions. That I think is huge. And other libraries on the Python side of, I mean, those I think are probably the most exciting things that are kind of out there right now. Someone is asking, what kind of projects have you used Dask in? So I've used it in cases where, I mean, general ETL type work, mainly to keep everything within Python. It can make things like testing much easier because you're just testing Python functions at the end of the day. And also on the ML side of things, you can parallelize through Dask where the algorithm supports it. I mean, not all ML algorithms are kind of easily parallelized, but where you can do it, there is a pretty good integration with libraries like scikit-learn. But yeah, I've used it more kind of just on the, if you need to process a lot of data in Python, and you don't have, especially if you're working with a team and not everyone is a Spark expert. In my experience, people can work with Dask much more easily.
So let us know how everybody's doing. Did you finish it up? Were you able to get through the exercises? Give us a bit of a pulse check. You can throw it in the chat. Tell us if you got stuck.
Yep. Yeah, I see someone else has a question about map reduce problems. So for this, I mean, so basically, since Spark is built on top of Hadoop MapReduce, I mean, basically a MapReduce problem is going to be something where you can apply a function to the same function to data in parallel. So like if you have a list of data and the outputs of each call are independent, you can parallelize that by, let's say in the simple case of you have 2 CPUs, you run pass half the data to one CPU, the other half of the computation gets run on the other CPU. And so if you're just doing something like add 1 to everything, the map operation is going to be take this list of data and map the increment by 1 function. And you can do this in parallel easily just by dividing everything and splitting everything up. Filter is can work similarly to map, and where you're applying some sort of test that is indicating whether you should, like if you're incrementing something, if you wanted to only increment the odd numbers, say, that's a filter operation. Again, this is going to be something that you can kind of naively parallelize just by splitting your data up across the number of cores you have. Reduce gets to be a little trickier. Reduce is when you take more than one data element and combine it into one. So you can think of adding two numbers together is a reduction operation. And so generally you're going to do something like you're starting out with a total. And so if you have a total of 10 and you're going to add another element to it, so then you'll come with your total plus 5, say, will give you 15. And so basically anything that's using MapReduce is at some level going to be built on top of these different operations. And that's kind of the lowest level primitives you're going to have. So basically you're going to have to shoehorn everything into these operations, which may make certain kinds of computations or things where you're doing like iterative computation challenging, which is kind of why one of the reasons why Spark was created in the first place is that like doing iterative computation in MapReduce, you have to write everything out to disk, read it back in, things like that. So, I mean, we haven't gone into this as much today, but in Spark, I mean, your lowest level of execution is an arbitrary Python function. So it doesn't necessarily have to fit into, it doesn't have to be map, reduce, filter, or reduce. It can be any of these. So, or it's just a Python function. So you have all of the flexibility you have of Python within Dask. There's not a restriction on what your primitives are in that sense. So, and there's trade-offs in that, because if you know everything is map, there's a reason that it's map, is they did it based on MapReduce, is that these are things that are generally parallelizable in a known way. Whereas with Dask, since you have more flexibility, you have the kind of Dask scheduler may have less opportunities for parallelization, or it may have to work harder to be able to parallelize your data. So there's, again, there's always trade-offs, but the benefit you have is that flexibility. Hope that answers the question. All right, well, let's work through these. I don't know if we can do like a thumbs up or something like that, or whether people are done or not. But I'll go through them anyway on my end. Okay. And I am just going to run these. So you're not going to see any output in the dashboard here, because I'm just going to run these directly using the non-distributed scheduler, which, I mean, again, is something we didn't talk about too much today, but we get into a little bit more in the longer course, is that Dask does have these different schedulers available, though in general, the rule is going to be use the distributed scheduler, but in cases where like you're on Binder or something like that, you can't use it. The least amount of work is just using this in-process scheduler here. Or I guess the proper name is the non-distributed scheduler, because it can use processes or threads. It can actually run within the same process here, which can also be useful for testing. So what we're going to be doing here is there's this payroll data that we have from New York City data here, and we're going to take a look. We have these 3 CSVs here, and we're going to calculate the base salary of all or the mean base salary of all of them. So we're going to iterate over all of these for that in glob. Oh, I already did this for you, so. We're going to read the CSV in. So we're going to keep track of all these data frames here. And so since we're calculating the mean here, and we're going to do this incrementally, what we're going to do is just calculate the sum and number of rows of each of these. So, well, all we really need to do is keep track of n and the sum. So we'll do that. So we're take n plus equals dat dot shape 0, and then s plus equals dat base salary dot sum, and then this should give us the answer. So that should do the trick there. And so doing this with Dask, we can just use read CSV with the payroll glob here. And since everything is lazy, this is not going to do any computations for us to start. And we'll see that we have 3 partitions here. This is going to be because each one of these is small enough so that per file we only need a single partition, but we're going to have 3 files. So there's 3 files, there's going to be 3 partitions. And now if we calculate base salaries, the mean here, and we're going to have to do compute here, keep in mind. If we time this, we can see that it's going to be similar in time here to what we have more CPU time, but less wall time. So these files are pretty small. So in this case, you can see that if you're not working with a ton of data, there's going to be overheads to parallelism that may not necessarily be recouped by Dask. So you have to make sure that you have a large enough problem that it makes sense to use parallelism always. All right, so let me just save this here first. And we're going to visualize our task here. And so you're going to see here that how this is working is we're going to read each CSV separately. So these are separate independent parts of the graph. So these can be done in parallel. And then within each series, we can actually, again, calculate sum and the count independently. But then these are going to separate components here. So we have to aggregate the counts and we have to aggregate the sums. And so basically what Dask has done for us is replicated what we coded out by hand, except in a serial fashion. So here we're not doing anything parallel, but Dask was able to put this together and find out the opportunities for parallelism for us directly. So, and again, in this case, the amount of data that's in here is small for the purposes of teaching the course, but if we were working with larger data set, having this parallelism available to us would be a benefit. And now, so next we're going to calculate max on overtime hours. So if we look at payroll.ot hours, if I spell hours right, and then we're going to visualize this. I think I'm just going to show you don't have to do rank direction, but it's usually easier to see left to right, at least in Binder. And so these 2 graphs are going to overlap here because Dask is not going to persist this underlying data from disk in memory. So we're going to be reading the CSV again and getting these items out again. So again, this allows us to operate on larger than memory data sets. But if we're repeating calculations on the same data set, like a DataFrame, a lot of times, we're going to want to persist that to memory. So we can do that now, actually, where we can payroll call persist, and note that persist does not have side effects. So if you just call persist and don't assign it to anything, it's not going to do anything. So generally a common pattern you'll see here is that it actually is going to assign it in place essentially. And so if we visualize this here again, now we're just going to have these three rectangles, which are going to be our data frames that have been stored into memory. All right, any questions on any of this?
There was one that I wanted to just mention. That was everybody's going to get the link to the recording. And then we're also asking about the slides. And I think that is in the GitHub repo.
Yeah, so the slides here, these are all actually just Jupyter notebooks. So they are all in the GitHub repo, and they will all continue to be on there.
Perfect.
And I think they are open. Yeah, I mean, it's all open source. I mean, these are all distributed under a Creative Commons license. So you can use them for your own non-commercial uses. Like if you want to teach this course for free, you feel free to use them as well. So just cite them.
Teach your colleagues.
Yeah.
Tell your friends.
Yeah, and favorite the repo too, so helps other people to find the code. Up in here, you can just star the GitHub repo in here if you think the materials are good. All right, well, we have time to go through the second part here that I wanted to demonstrate, which is how to use the dashboard when you're working with Dask. So so far we've really done kind of a crash course in working with the DataFrame API. So in theory, you should be able to kind of conceptually understand a bit of how data frames are represented within Dask, what Dask does at a high level, and work with these. In the longer version of this course, we would actually start specifically going into how the Dask data frame and pandas data frame APIs differ, because there are certain things that are harder to do with distributed data frames than with in-memory data frames. Like when you get into things like merging and things like that, there are different considerations you have to take into account for distributed data, because you may have to shuffle data over the network, which is much slower than doing it in memory. And so you also end up with issues of you have to know where the different parts of the data frame are stored. Versus in memory, everything is in memory in process. So this leads to some considerations that need to be taken into account. But again, it's probably another hour and a half of going through that part. So if you're interested in learning more about the differences between the two APIs and what kind of operations work quickly in Dask and other ones you need to be put more thinking into. And I mean, again, this doesn't just apply to Dask as well. It's also going to be any distributed computing framework where you're doing like a merge or things like that. A lot of these also apply to Spark as well, because at the end of the day, they're solving the same kind of physical computation problem. All right, so we're going to skip that one and go to slide 3, which is Dask performance here. So I'm actually going to load this here, and I'm just going to connect directly to the existing scheduler here. see. Actually, it's probably just easier just to shut this down here. I'll show everyone how you can connect to an existing scheduler here, because we have started. Like, the benefit of Dask is that you get everything starting directly in memory, or you can have everything starting directly on your laptop with one line of code. But again, if you're doing this more generally, a lot of times you're going to have a cluster you're going to want to connect to. So since we have an already running cluster, we can connect to that directly. And we'll see this is our cluster that we started before. And again, if you're running this just on a single laptop, a lot of times you would just start this up in the script. But if you're connecting to an external cluster, your client is probably going to be hitting that. And we're going to be working with this payroll data again here. No, I'm looking at the wrong one. That's why. It's like, I didn't think we were working with the payroll data here again. All right, so I put in here actually some computations so we can better see what the graph is doing, because these other ones, if you're working on a larger data set, you can see, but those aren't the most friendly for having people follow along. So what we're going to do is we're just going to generate a bunch of random numbers and compute the sum of all of them. And so this is going to be an array that we're creating. And so you can see in the background now that things are starting to happen. And I'll probably go through this twice while it's running just to show everyone what's going on here. Well, it's actually, let me go to this one here, because this actually has some other things going on too. So what does this all mean? So if I'm going to start with this task stream here, because this is always a good place to start when you're working with Dask. So each rectangle represents an individual task, and generally a task is going to be a function, Python function call. And everything that is the same color is going to be the same function. So you can see that all the blues here are random sample sum. Each bar is going to represent a separate thread of execution. So this can either be an individual. So Dask, how it is going to work in the distributed context is that there are going to be multiple workers. So if we look back here, we'd see in the client that we have 4 workers, and it's saying that we have 8 cores. Now, my laptop only has 4 cores, but what it is actually telling you the number of threads total. So it's not really cores per se, but it's the number of workers times the number of threads in each. And I guess in theory, you could have different number of threads within a worker. But basically, here's the total potential concurrent executors. And so each one of these is showing, we can think of it basically as an independent worker here. We'll just assume that's the case, even though there could be multiple ones on the same worker. Now, the graph here is a timeline. So we're going from left to right in terms of time passing. And any place that the bar is filled in, that indicates that that is when this computation is happening. If we zoom in further, we can also see that there is some white space here. And so white space is indicating time where the worker is just waiting. So it's not actually doing anything. It's probably waiting for the next task. And we can see some of the smaller tasks in here, like between random sample sum here. Or this actually, no, this is not a separate task. If you zoom in enough, you see that it's actually just white space. So most of the time, and in general, we have to zoom pretty far to get places where it's not doing anything. So for the most part, this is saturating the workers. This is pretty good. But we can see of some of these other tasks here, like this is calling sum versus random sample sum is going to be a different function in there. And again, this is just, it's a different color here because it's a different function. The color that is always going to be, and let's look, this purple one here is going to be sum partial. So this is calculating the sum, but not at the full level of everything we want to aggregate to. The other thing, the only thing that's going to be constant in color is going to be data transfer, and that is always going to be shown as red here. And so here we can see that these red blocks here are places where data transfer is happening between workers. And this is going to happen because since we're running in a distributed fashion, in different cases, we're going to have to receive data either from other workers or the scheduler, and we're going to have to transmit data to other workers so that they can continue their computation. And so here, for the most part, since this is going to be a problem that's fairly easily parallelizable, I mean, there is going to be data transfer, but it's not going to and shouldn't dominate the work we're doing here. If we look at the end, we can see where you'll notice a lot of times towards the end of the computation, there is going to be space, larger spaces relative to everything. And this is going to be because the different tasks are finishing up more. Some are finishing more quickly than the others. I mean, this isn't a lot of time. This is half a second here. So everything basically finished relatively around the same time. But it's not going to be exact. So some are going to finish up there's some before others, and then they have to transfer the data. And so in the end, all of our data is going to need to end up kind of in one place to be able to calculate the final result. And so we'll see our final answer is only going to be on this one worker here because everything at the end has finally been transferred here. And so towards the end, we're going to be waiting because we need to get back all our results from the different workers. So let's take a look again. I'm going to run this actually again, just so we can look at some of the other parts of the graph here. So another part of the graph here is to look at is where our tasks are processing. And so this is going to tell us what the different parts of the tasks are. And so we can see here for read CSV tasks, since these are a dark color here, that means that these have all been completed. The ones where we have a lighter bar that is moving across, well, see, this is the challenge here when you go through it. These are going to indicate ones that are tasks that are ready to run but have not yet been executed. So this means that we have work that is able to be done. If we had more cores available, we could do this more quickly, but we don't. So this is not necessarily a bad sign to see. It just is work that's queued up. And when we see things that are purple, these are tasks that have been in memory and not yet released. So that means they are computed, but we have they're still in memory. Run this one more time. And then here we can see ones that are still, again, we have our tasks that are ready to be run. These ones here, for example, some here you'll notice has less, since it's lighter gray here, there are less tasks that are queued to be run because the sums are being calculated in more intermediate fashion here. But things like the random sample sum, that generally we have everything ready to go to begin with. We just have to be able to actually run all of it. Now, if we go down here a bit more, we'll see that we have in the slides or notebook here, I have a bit more description of what we talked about also in the bottom of the worker here. And as I mentioned, the gray bar is going to indicate when they're ready to run. The darker color bar here is going to be whether indicating that this is in memory on the worker. And once the leftmost part of it has indicated the lighter part that the tasks have been run and then released, that they're completed. We'll also take a look at another graph here where there is a tool for, so Dask has some built-in helper functions for generating time series or other testing data. And so we can run the graph against these and see that some of these operations are going to run, or one thing I'll note is some of these operations here don't necessarily run more quickly, even on Dask, like some of the Dask specific approximations here aren't necessarily faster than some of the non-approximate versions. I think this was just a interesting note I had here. But again, on these here, you'll see that even on these, we have fairly good utilization here. One thing, we're running close out of time. So one thing I actually want to show is a case where we don't have great utilization, when this might give it to us here. So you'll notice here, if I change the chunk size on our array, which is how Dask processes it, to be larger, we're not going to actually be able to use all of our cores effectively. And so you'll see then that we just filled this in here, and you can see how much white space we have in this generating here. And we can actually make this even worse if we reduce the size even further. This is going to take a while to run here. So I'll stop this here and run it again.
Sorry, Dan, I didn't catch why that was.
So what's happening here is, so when we specify, when we're creating this random array here, what happens is we are telling it how many different tasks should we create? Should the tasks be bigger or smaller? And so if the tasks are too small, the workers are going to be finishing them too quickly. And so most of their time is just going to be waiting to get the next task assigned to them. So this is an issue where if the size of your work is too small, for example, you're not going to have good utilization of your underlying workers. And you can see this in the graph here, where generally where you have lots of white like this, it's going to be an indication that you're not utilizing your cluster well. Like you want everything to look like the other one did, where all the bars are kind of going all the time. If they're not, it means that your workers are generally waiting. They're doing more waiting than computing. So, and like a simple reason for that a lot of times is that the amount of work they're doing is too small. So if they can, like, let's say they just had to add like 2 numbers together, and that was your work. And then you have to wait for the next 2 numbers for you to get. Like calculating the sum of 2 numbers is very fast, but the network is very slow, very slow relative to that. So you could probably calculate, you could add like 1 million numbers together in only a slightly larger amount of time relative to the amount of time you'd be waiting. So this again gets, I mean, this is going to be one of this, and you can see here, this computation is still going, and we ran it before. And yeah, you see this at the end here, like this is all just data transfer. So if you're just adding 2 numbers, like let's say each time, most of the time, all you're doing is sending those numbers around that result and waiting for the next 2 numbers, where like the sum of 1 million numbers, you only have to send 1 outgoing result per 1 million numbers you get. So it finally finished. But again, this is going to be, if you see something like this when you're working with Dask, it's going to indicate that's probably going to be the case, that your computation is too fine-grained. So there's more in the utilities, these utilities here to go into, but that's a quick intro into kind of top level of understanding is that what these flashing lights actually mean. So I think I'll close there and take any questions people have.
While we're waiting for questions to pop up and for you to type them in, Dan, I want to say big thank you. This has been a very insightful experience. I have learned a lot about Dask, and especially because I was very unfamiliar with it before coming here. I was unfamiliar. I had no idea what it was really. I knew the basics, but this has been a deep dive into it, and I feel like I can leave saying at least I have a better understanding. I have a more basic, high level knowledge of it and could probably hack something together on it.
You now probably know more about Dask than 95% of people.
Perfect. So if nobody's got any questions, I will just ask if somebody wants to reach out to you, what's the best way to do it? I know you're in our Slack. So
yeah, in the Slack, or you can also hit me up just by email. I'll put it in the chat here. It's just dan@enplus.dev, or you can hit me up on LinkedIn too, or in the chat.
Cool. There we go.
All should be good.
Yeah, if anybody has some extra questions that you can think of afterwards, feel free to reach out to Dan. I really appreciate you doing this for us. This has been a first, and it was groundbreaking today. I love it, man.
Do it, and thanks everyone for taking the time to join us.
Yeah, big thank you to everybody that stuck through it and did the exercises and learned about Dask. And yeah, would love to hear if anybody actually uses this, what you've been using it for. So throw that in the Slack, tag both Dan and I, because I think that could be really useful.
There's also a Dask developer survey out right now on the Dask website. So if you are interested in using Dask or currently using it, then please fill that out, as it helps them gauge the number of people using it, which they have actually received some funding from the Chan Zuckerberg Foundation for Dask support. And I believe, I'm not sure of this, but I imagine in a lot of cases that the size of the community can help in getting these different grants, and also helps to guide what they work on going forward, as areas of interest to different users will indicate where they should focus on.
There you go. So go and start on GitHub, and I will be sending you all out a link to this recording in case you want to go back and say, how was that done? Which one was it? Why is it not utilized properly? Whatever it was. And we will be seeing you next week. We have more meetups. On Wednesday, we'll be back for another meetup. And that's about it for today, folks. I appreciate you being here. Again, Dan, thank you. This has been awesome.
Demetrios, thanks again.
See you later, man.
Bye.